So number one, finding numbers. The sum of two non-negative numbers is 20. Find the numbers if A, the sum of their squares is as large as possible, as small as possible, and B, one number plus the square root of the other is as large as possible and as small as possible. So first thing that we need to do is figure out what the two numbers are. So their sum is going to be 20. So if, let's let x be the first number, then 20 minus x would be the other. So x. Okay, so for part A, it says the sum of their squares is as large as possible. So f of x, we want the sum of their squares. So x squared and 20 minus x squared. And so this gives us x squared plus 400 minus 40x plus x squared. This is just f of x. Let me just clean this up. So we get 2x squared minus 40x plus 400. So now I'm going to do the derivative. We get 4x minus 40. So when we set this equal to 0, we get 10. Now, one of the things that we didn't consider from the beginning, if you look at two numbers and they're non-negative, so if we're looking at two numbers that have a sum of 20, the domain has to be 0 to 20. So the smallest one of them would be 0 and the largest would be 20. So consider those as our endpoints. So for the sum of their squares to be as large as possible, we can do a quick so we're going to create a number line. So I think this is 0, this is 20, and right in the middle we have 10. So we're going to pick a test value, say 5. I'm going to plug that into the derivative. So that's going to be 4 times 5 is 20 minus 40, so we get a negative. And then plug in something between 10 and 20, say 15, and we get positive. So it's going to go down and go up. Okay, so what this means is that would be a minimum. Since this is an endpoint, that's a maximum. That's a maximum. So again, it's the sum of their squares is going to be as large as possible. So for part A, well, if one of them is 0, then the other one has to be 20. So 0 and 20. And then for B, if one of them is 10, then 20 minus x, the other one has to be 10. Oh, I'm sorry, that was still for part A. So as this one is large as possible, and this one is as small as possible. Okay. Now for part B, it says one number plus the square root of the other is as large as possible and then as small as possible. So we still have all of the same information from number 1. So we're going to be able to use all of the information, like 20 minus x is the second number, domain is still 0 to 20. We just are probably going to get a different critical number. So one number, so it's going to be f of x. So we have one number plus the square root of the other. Now there's two ways I could do this. I could do x plus the square root of 20 minus x, but it doesn't really matter which number you put under the square root. You just have to put 1. So I would actually write it as 20 minus x plus the square root of x, just because that's easier to do the derivative. We don't need to worry about doing a chain rule or anything. So I'm going to use this one, and I'm going to rewrite it as x to the 1/2. So when we take the derivative, we get a negative 1 plus 1 over 2 root x. So I'm going to set this equal to 0. Okay, so when we set this equal to 0, we get 1 equals 1 over 2 root x, so we can just do the reciprocal. So we get that. We get 1/2 is equal to square root of x. So then I take both sides and square them. We get 1/4. So that's our critical point. So we are going to test our critical point. So now here's f prime. Again, we have 0 and 20, and we want to test 1/4. So basically, when we plug in something smaller, say like 1/16, so then we get 1/4. 2 times a fourth is 1/2. 1 over 1/2 is 2. 2 and negative 1 make a positive. And then plug in something bigger, and we're going to get a negative. So it goes up, and then it goes back down. So that means we have a max at 1/4. So we have the largest or as large as possible will be 1/4, and well, if they have to add up to 20, it's just going to be 19 3/4. And then as small as possible, that's going to be 0 and 20. Okay, so the next one is going to be number 3. I think so. Yes, number 3. So it just goes odds. So number 3, maximizing perimeter. What is the smallest perimeter possible for a rectangle whose area is 16 square inches, and what are the dimensions? So let's draw a picture here. Okay, so the area is 16 square inches. Here's our length, here's our width. Okay, or that's fine, we can do length times width. So we have area is equal to length times width, and we know the area is 16. So remember, I can't have two variables. I have to convert one of them and change it into a different variable. So it doesn't matter really which one we want to change. Let's say we want to divide by L. So W is 16 over L. So I'll just kind of put that in here. Now, I want to... Okay, so we're back. And number 3, we are looking for the smallest perimeter. So we know perimeter of a rectangle is 2L plus 2W. But we only want to have one variable. So it's going to be 2L plus 2. And W, we're going to substitute in the 16 over L. If you don't like the L, you can always change that over to X if you want. So we can make it like a 2X plus 32, and then we could do X to the negative 1, just to make it easier. So when we do the derivative, we get 2 and then minus 32X to the negative 2. I want to find the critical points. So we put that over x squared. So we get 32 over x squared equals 2. So 2x squared equals 32. X squared equals 16. So x equals positive or negative 4, but obviously only positive 4 makes sense. Now, this one doesn't give us an option for large as possible or small as possible. And, you know, if x is equal to 4, I mean, we could double check this. Obviously, we don't want to have a negative measure. But if we were to plug in something between 0 and 4 into the derivative, you know, plug in, say, 3, this is obviously going to give us something negative. You're done with your homework? Everything? Okay, go. Give Owen his too. So, I'm sorry, I think I was reading the wrong problem, but we're looking for the smallest perimeter. So it's going to go negative and then go to the right of 4. So, say 6. So we'll have 32 over 36. And that's going to be positive. So it's going to go down and then up. So this is going to be a minimum. So for number 3, what is the smallest perimeter? So think about plugging in 4, right? So that's going to be 2 times 4 plus 32 over 4. Right? So 8 plus 8 is 16, and that's going to be 16, the units are inches. And then it says, well, what are the dimensions? Well, the dimensions, turns out that it's actually a square, because when we get 4 by 4 will give us 16 square inches. So 4 inches by 4 inches. Okay, the next one is number 5. So in number 5, we see an inscribed rectangle. Okay, so what we need to do, kind of, actually, let me just copy and paste from our notes real quickly, or from the book, excuse me. And just make it easier when I have to do the problem. So here is the picture that we want. So I'm just going to make a quick. Okay. Oops. Okay. Okay, so here we go. We want to maximize, or actually there's a couple of questions that we want to write in here. So here's a rectangle. It's inscribed in an isosceles right triangle. Okay, and we can see that, like, for example, oops. Like, for example, we can see this is the point, -1, 0, and this is 1, 0. And not only that, but if this is a right triangle and it's drawn like this, then actually both of these end up being 45, 90 triangles. So if this is one here, right? And then actually these would be a length of square root of 2, just kind of a side note there. All right, so we want to, let's look at part A. So part A says express the y-coordinate of P in terms of x. Okay, so we encountered this problem when we saw in the notes packet. We wanted to put a rectangle under the sine curve. So wherever x is, so like we look at this distance over from 0 to some unknown value of x. Well, what is this going to be? this is going to be y equals whatever this equation of this line. So when we had the sine curve, it was just y equals sine x. But this one, we want the equation of this line. Now, why did I talk about this length? Well, this is going to be the point 0, 1. So if I have 2 points, 0, 1, and 1, 0, I can write the equation of that line. That line is going to be, it has a negative 1 as the slope and a y-intercept of plus 1. So this y is actually going to be, this is going to be the height of, that's going to be the height of my rectangle, whereas here, if over from 0 to here was x, then all the way across, 2x is going to be my base. Okay, so let's write this in. So p is going to be x comma negative x plus 1. Next it says b. Express the area of the rectangle in terms of x. So as I was just showing you, the base is going to be 2x and the height is negative x plus 1. And then we can just multiply that out. So and we can write it as a function of x. So negative 2x squared plus 2x. So there's part B. And then for part C, what is the largest area the rectangle can have and what are its dimensions? And so we're going to go through, find the derivative. So it's going to be negative 4x plus 2. Set this equal to 0, so we get 4x equals 2. So x is a half. Now just knowing you know, that the problem itself is a negative x squared, I know that's going to be a maximum. But you can also just make the number line real quickly. Just to kind of save some time, you could do the number line. You will see that it's a maximum. So if we're looking for the largest area, if this is going to be 1/2 here, we can just plug in 1/2. And let's see, what do we get when we plug in half there? So that's going to be oh, we get a half. Is that what we get? Negative 2 times 1/2 squared plus 2 times 1/2. Because this is going to give us a 4th times negative 2. Yeah. And then the dimensions. Well, the base, if x is a half and the base is 2x, it's going to be 1 by 1/2. Because if you plug in negative a half, that's what you get there. Okay, next one is number 7. So number 7, optimal dimensions. You're planning to make an open rectangular box from an 8 by 15 piece of cardboard by cutting out congruent squares. Okay, so this is basically the same thing that we had in our notes packet. So you start with a rectangular piece and it's 8 by 15, and then it's like you cut squares out of the corner, so x. So our volume is what we want to look at here. So we want largest volume. So this is going to be 15 minus 2x, 8 minus 2x, and then times x. And then I would probably multiply this all out just to make it a little easier when we go through the process of the derivative. So we have 120 minus, let's see, minus 30x minus 16, so minus 46x, and then plus 4x squared. So we want to multiply this whole thing by x. So 120x minus 46x squared plus 4x to the third. So I want to do the derivative. So I get 120 minus 92x plus 12x squared. I'm going to set this equal to 0. I'm going to just rearrange things. Okay, now I can actually simplify this. Everything can be divisible by 4. So I get 3x squared minus 23x plus 30. And then let's see. Okay, so factoring this, I believe 3x minus 5 and x minus 6 will work. Yes, okay, so my critical points are going to be 5/3 and 6. However, 6 doesn't make sense because, you know, just plugging it into the 8 minus 2x part, you know, remember if I'm taking away an x here and an x here, taking away 6 on each side of a cardboard that's only 8 inches across, that's not going to work. Okay, so I want to make sure, so you can, again, you can double check that that critical point is going to be, that's going to be basically, since it's an x squared, it's the smallest, or actually no, yeah. We want 5/3. We want to cut off that portion so that we have the largest possible volume. Again, you can verify that with a calculator, but or a number line in a calculator and plug in 5/3. And let me just take a look to save time. So our volume is going to be, comes out to about 90.74 cubic inches. And then the dimensions. Okay, so the dimensions are 5/3 inches by 14/3 inches by 35/3 inches. Okay, number 9. Number 9, the best fencing plan. So a rectangular plot of farmland will be bounded on one side by a river. Okay, so here we have a rectangle. And it's bounded by the river. Okay, and it's on the other 3 sides by a single strand electric fence. So you have 800 meters of wire at your disposal. Now, in this case, normally if you think about the perimeter, if you think this is L and this is W and this is W, so 2L, oops. 2L plus just 1W is going to be 800 because that's how many meters we have for a round. And then I can solve for L or W. Again, it doesn't really matter. If I solve for W, we have 800 minus 2L. And then, like I said, if you don't like to work with L and W and you want to just change that all to X, you can. So I can say, you know, instead of L, we can use X, because when we talk about the largest area, so area is going to be the base times the height. So if I want to write this in terms of X, I have 800 minus 2x times x. So we have 800x minus 2x squared. I want to do the derivative. So I get 800 minus 4x. So set that equal to 0. And then we get x equals 200. So the largest area, again, you can verify this, make the number line, show that that's going to be the value that's going to maximize the area. So then we want to plug that into area. So area is going to be 800 minus 2 times 200, and then times 200. So it's just 400 times 200. So we get 80,000. And the units are meters squared. And the dimensions are, okay, so 800 minus the 2 times 200, that's going to be 400, so it's 400 by 200. Or 200 by 400. Okay, number 11. Designing a tank. Your ironwork has... Okay, so designing a tank. Your ironworks has contracted to design and build a 500 cubic foot square based open top rectangular steel holding tank for a paper company. Okay, so it's a square base. Something like that. Okay, so this is a square base, and so we don't know what the height is, but we do know it holds 500 cubic feet. So the volume, which is going to end up being x squared times h, is going to be equal to 500. So if I divide both sides by x squared, the height is 500 over x squared. So the tank is to be made by welding thin stainless steel plates together along their edges. As the production engineer, your job is to find dimensions for the base and the height that will make the tank weigh as little as possible. So what dimensions do you tell the shop to use? And then so that's part A. So part A is going to be, since we want to use, we want it to weigh as little as possible, that means the surface area. So how much material is used as the surface area. So again, this is going to be open top. So usually surface area is 2 times, just so you know, it's 2 times the area of the base plus perimeter times height. That was the formula that you learned about prisms in geometry. But we only have one base. We only have this base. So that base is going to be x squared. The perimeter of the base is 4x times the height, which is 500 over x squared. So we have x squared plus, it's going to be 2,000 x to the negative 1. So I'm going to do the derivative, 2x minus 2,000, it'll be x to the negative 2. So we want to set this equal to 0 to find the critical points. So I have 2,000 over x squared, move that over, equals 2x. So I put that over 1, we get 2x cubed is equal to 2,000 when we cross multiply. So x cubed is equal to 1,000. So we take the cube root, and we get 10. Okay, so again, you can verify that 10 is going to be a minimum. So if x is going to be 10, if we go back to the dimensions that we need, it's going to be 10 feet by 10 feet by, and then plug in 10 feet, so that's going to be 500 over 100, so that'll be 5 feet. And then for part B, it just says briefly describe how you took the weight into account. You could just basically say if you have the surface area and you have how much it weighs per foot.
First to take it back.
So you're basically, you could just multiply that out. Okay. Then for number 13. Designing a poster. You are designing a rectangular poster to contain 50 square inches of printing with a 4-inch margin at the top and the bottom. So you have a poster and you want a 4-inch margin. So it has 4 inches. So this is your 50 square inches. And then kind of imagine it's like 4 inches here, 4 inches here. So it's going to be like 4 inches on each side, on each end. Oh, no, I'm sorry. I didn't read the whole thing. So it's a 4-inch margin at the top and the bottom and a 2-inch margin at the side. So actually, let me just rewrite this. So we'll say this will be 2 here and this is 2 here. So what overall dimensions will minimize the amount of paper used? Okay, so the printed area, we already said was 50 square inches. Okay, so just, we'll say the inside rectangle, right, has an area of base times height. So we have 50 is equal to B times H. So we divide by H. Again, it doesn't matter which one we use. So we have base is 50 over H. So I'll just say that this is, instead of base and height, we'll call this X, and then this will be 50 over X. So now this way is going to be X plus 8, because if this is X, we want to add 4 on each side. And then this is going to be 50 over X plus 4, because we're going to add 2 here and here. So now we want to look at the outside rectangle. And that's what we want to focus on. So we want to minimize the amount of paper. So our area of the outside rectangle is going to be 50 over X plus 4 times X plus 8. So we're going to FOIL that out. So we get 50 plus 400 over X plus 4X plus 32. Okay. So we get 82 plus 400 over X plus 4X. Now, I want to take that, and I want to do the derivative. So I get negative 400 x to the negative 2 plus 4, and then we're going to set that equal to 0. So I get 400 over x squared, and that's going to be equal to 4. So I get 4x squared equals 400. Divide by 4, we get x squared equals 100. So x equals 10. So if x equals 10, we go back to the picture. So our overall dimensions are going to be, so if x is 10, we look at 50 over 10 is 5 plus 4, so 9 by 18. Okay, number 15. Two sides of a triangle have lengths A and B, and the angle between them is theta. What value of theta will maximize the triangle's area? So we have A and B, and the angle between them is theta. Okay, so what value of theta will maximize the triangle's area? So I'm going to give us 1/2 AB times same sine of theta. Okay, so when we go to solve this, we get, we have to do the derivative, and we consider A and B. A and B are going to be held constant, so we kind of treat this as like just a coefficient here. So it's going to be 1/2 AB times the cosine of theta. And then we want to look at where this is equal to 0. Since A and B can't be 0, we look at where cosine is equal to 0. And we get theta is equal to pi over 2. So for number 15, this is going to be our answer. Again, do a number line and just verify that that is going to maximize, that's going to give us our maximum value. Okay, so now that was 1 to 15 odd. Now we go to 21. So 21 is inscribing rectangles. So I'm going to, I'm actually going to pause this, and I'll continue with this on another section.